Okay, so as usual, we'll go through a brief discussion of what was covered in this week's content. So the amount of content was not as much as the usual weeks. There were only 1.5 hours of video content, I think. But the two topics that were covered are deep and maybe difficult to understand on your first run. I still hope the first part, which was talking about the coherent, the architecture of the receiver. So I hope that part was clear to you. But the remaining part, which was discussing about these impairments and simulation of the impairments and subsequent correction of those impairments using digital signal processing techniques. That part could be a little difficult, but don't worry if you don't get everything. Just try to get the gist of the concepts. So this was the first part basically. So for each of the discussed topics, you have to keep in mind what is the architecture, like what are the components and how are they connected. So how are they connected, that you have to keep in mind. And according to that, you have to be able to write how the electric fields are adding up, how that translates to changes in power, and power in turn can be detected using photodetectors. So that how that translates into current values, then from those current values, what can you tell? So that whole sequence you have to be comfortable with. So there are some, like for all of the architecture shown in class, we have discussed how the equations have come, and the assignment is also asking you to do the same thing basically. So they've given you some transfer metrics for a 90-degree hybrid in assignment, and you're asked to find out what are the current values and so we started our discussion this week with a coherent detection, and the equations you have seen from I think week 9 content, week 8 or week 9, I'm not sure, but before discussing nonlinear effects in fiber, we talked about this, how the equations come up. So if you want to brush up the concepts, you can look at week 9 content also. Basically, you're instead of summing two electric fields, here what you're doing is using a 2x2 directional coupler, and then the outputs of them are being fed to two identical photodetectors, and then we take the difference of currents to see how that has affected. Like we model the input electric fields as these two equations. So there is some amplitude and like a frequency and a phase. So we don't go in depth into how this 2x2 directional coupler, this equation, why does this J come in? I think I saw some questions. I'm not sure whether it was in the forums, but so this J comes from just the structure of the directional coupler. Like when you solve the couple differential equations, which is like out of scope of discourse. So we have not discussed, we have directly given you this matrix. But for example, like directional coupler is like it has some coupling region, like where the cores of the two fibers are very close, and the evanescent fields where you saw the mode profile, no, it like amplitude of it is uh, falling exponentially outside the core. So that part overlaps with the other core, and that induces a electric field in the other core. So this was like briefly touched on in the last week's content. So because of like this kind of coupling, if you solve the a couple differential equations, you get this uh, J term. Instead of this structure, instead of this 2x2 directional coupler structure, if you just use a power splitter, then you would not have this uh, uh, if you use this kind of structure, a 1/2 splitter, then you would not have this J term. So why it comes, if you want to see the math behind it, you have to, I mean, all of the textbooks should have the description, but like it is not a concern of discourse. So, so that is the origin of this J that we're not discussing. Then what 2x2 couplers do is described by this matrix. So if the inputs are these, output you can get using like this matrix. And instead of using matrix, if we like expand and see what is happening in at E1 and E2, you expand it into these equations. Then from these equations, like how do we get the currents? Currents are basically coming from like currents are coming from in that weak 8 equation, how the photodetectors work. So current will be RD times optical power in. And optical power in turn is proportional to the electric field mod square. So that is where I think someone asked in forum like how we are getting this current equations. This is simply just RD times the power, and because like we are talking about two current values, we're putting it in this kind of form. Just I1t is equal to RD times E1t mod square. That is all. Like there is no magic. And how to find the mod square? You just substitute this and find the mod square. So just expand using a plus b whole square. But keep in mind that there can be complex values. And like our concern is this part, and to extract that we can use the balance detector system. So I1t minus I2t. You will have this expression. AS is the electric field amplitude, which is proportional to square root of power. That is where all these are coming from. Then this was the first structure we discussed, this balanced photodetector structure. Then subsequently we keep adding on that structure. Like if you understand this structure, you should be able to understand what the other things are doing. So like in the same structure, if you use a like in this structure, we had to align our LO polarization with the receive signal polarization. If you want to either detect a dual polarization multiplex signal, or if you wanted to detect like without doing any alignment of polarization, you can use this polarization diverse coherent receiver. The structure you have to see in video. I have not added here. Similarly, then we talked about this phase diverse receiver, how to detect a phase. And instead of tracking phase electrically, like we can use this special structure where we can get this both like in phase and quadrature parts. There may be some errors, but we'll detect this sign, like we will detect like sine of this delta phi and cos of this delta phi. And this concept of 90-degree hybrid was introduced there. So ultimately what we'll be getting once you like check the structure for this 90-degree hybrid for both polarizations is that you'll be getting these four streams of complex data. So that data you can process using digital signal processing techniques. This is where we talked about this different kinds of impairments, what we have discussed. So initially during our discussion on dispersion, we introduced dispersion. Then here we mentioned frequency offset. So your laser that was modulated, the signal laser, is not at the exact same frequency as the local oscillator laser that you're using to detect for coherent communication. So that LO laser being slightly off from the scent laser will cause impairments, that is frequency offset. Then laser phase noise we have discussed using our discussion on lasers. Then we also talked about this polarization mixing. So you send two data streams in two independent polarizations, but because of the fiber birefringences and like different stresses and all, the two polarizations will mix inevitably. And what you'll be getting at the output will be a mix of the two polarizations. So so data from one polarization will go to other polarizations using some conversion matrix. You can think like the matrix will be of this kind of form. So if your input electric field was something like your output will be a sum of your X polarization into this term plus your input Y polarization times this term. This kind of mixing will happen. There are some properties of this matrix, like you don't need to worry about it, but basically we assume that the powers are conserved, and like this matrix is considered unitary. So its inverse is also unitary. There are some properties. So but using like some of these properties are useful in this polarization demultiplexing step. If you do it in DSP, I mean you have to do it in DSP. And we in class we showed, without much discussion, we just showed how the demultiplexing can be done using this constant modulus algorithm, which is like both this phase estimation, pollution demultiplexing. Those are happening using adaptive filters, where the filter coefficients are changed so that some error function is minimized. So in this constant modulus algorithm, we try to minimize the, if you're sending QPSK data in your constellation, you know that all of the constellation points should lie on the same circle. It should be same amplitude. So what you try to do is uh, due to mixing, what you will be detecting is something like so instead of receiving this QPSK data, you will be receiving some uh, like in your export data, there will be small part of Y polarization data also. So what we try to do is we try to change the filter coefficients so that this error caused by all of the received constellation points being away from the ideal circle, uh, like that error should get minimized. So that is how that is the gist of this CMA. Similarly, carrier phase estimation, you try to minimize how far the constellation points are going away from the ideal constellation points. Then frequency offset we do in usually do in frequency domain. You take FFT of the received signal and try to find if there is frequency offset, there will be peaks at uh, non-DC values. There's some doubt here, using this FFT technique, you don't necessarily need to do fourth power, but fourth power does good performance. So what we said in class was that um, so what was like you might be knowing this from a course in DSP, but we have not gotten in depth in this course. So if you have a signal and you sampling rate fs, when you take an FFT, the maximum frequency that can be represented is this fs by 2 here, and in negative side also minus fs by 2. And higher frequencies will get folded back into this range, and you will get some aliased signals. So basically, if you consider the real continuous time signal is sine omega t, but what we are doing is we're sampling it at t is equal to n times some sampling time, which is equal to n times 1 by fs. So to detect something without any ambiguity, what you need is this any signal's frequency spectrum should be within this range. If it goes outside of this fs by 2, it will be aliased, so you will get some fake representation inside this range, so which will cause confusion. So what we try to do in frequency offset correction is we if you're not taking any fourth power, then you'll be getting some peak corresponding to however much is the frequency offset, say not omega, this should be frequencies. Now, if you take fourth power, instead of getting this peak at offset corresponding to offset frequency, you'll be getting it at 4 times frequency offset. What we want is that 4 times frequency offset should be lower than fs by 2. So like maximum frequency offset that you can correct is limited by that, like the 4 times frequency offset has to be less than fs by 2. So like frequency offset that you can correct has to be less than fs by 8. There is some mistake in this end of the video lecture practice questions. Novamita said that there was some error that this is fs by 4. Some question is claimed. This is wrong. But like what determines what is the maximum frequency offset we can detect reliably, that is determined by this, like because of our sampling frequencies. And generally we like during the videos you can see how we simulate the effects due to some communication system. Like we are using all of the equations taught in the course itself. Like it is not some magic that you cannot do. You just consider a set of bits and you try to find out step by step like what can be happening to those bits, what can be happening to those electrical signals, how they're traveling through the fiber, and like how you then go ahead and correct for the impairments. So that is pretty much the content of this week. Are there any doubts and questions?
Sir, am I audible?
Yes, yes.
Sir, I need in the sampling frequency divided by 4 or 8, I need to do.
By 8 you need to do.
Okay, so 1 gigahertz divided by 8 it will be. It is written sampling frequency in the simulation is 1 gigahertz. So 1 gigahertz divided by 8 it will be.
Yeah, that is the maximum you can correct.
Okay, sir. Okay, sir.
And like, yeah, that is a like description, like why it is happening. Basically, using any FFT, wait,
From the discussion, it is clear, sir.
Yeah. That's pretty much
it is clear, sir. I'm only confused whether divided by 8 or whether divided by 4.
Yeah, it is 8. And like,
okay, sir.
So basically, there is this relation you need to consider. Like there is in time domain, there is this much time we are considering, and each of the points are say dt, and in frequency domain it goes to some my drawing tablet died, so I can write properly. So so basically this what is the extent of your frequency domain signal that is captured by this. What is your time domain resolution? Time domain resolution gives you frequency domain range, and time domain range gives you frequency domain resolution. Like there is this kind of a relationship. Like that is the like deal with FFT that you need to remember. That's all.
Okay, sir.
Someone is asking me, like, okay. If there are no doubts, like we can close. In assignment questions, they've given you this transfer functions, and you need to find out what are the currents, and they've clearly stated like find uh, I1 square plus I2 square something. And one confusion that might be that this may not be clear is okay. So in the like second group of questions, they've given you like 3 by 3 uh, hybrid, and it's like transfer matrix. Like it is given you this matrix. It has given you. So it has given you this. What does a 3 by 3 coupler do? Like, what does this function, like, what does this block do? It has given. What you're asked to do is like consider only like there will be 3 inputs and 3 outputs. What you're asked to do is like don't consider this third port. It is like said you can use a 3 by 3 coupler as some kind of a hybrid. What will be the errors in it? So like only use port 1 and 2. So basically in this matrix, like like you need to consider what is happening to only this section, I think. So if there is some ambiguity there, like that is the thing. Like don't consider third ports. Otherwise, the assignment is just asking you to like do some hand calculations so that you understand what is happening in the course. And the DSP part, like you don't need to go too much in depth. Like just understand the gist. How do we correct for chromatic dispersion? We just use the inverse of the channel that is like known if you know the length of the fiber. So chromatic dispersion, you just use inverse of the transfer function. For frequency offset, you do 4th power, and then again in FFT, you see what is the offset that is coming. Clock recovery is just clock recovery is probably not discussed in classes properly. Like it is checking which sampling point to consider for demodulation. Like in resampling, you have taken multiple samples for each symbol, no? Like which time spots to take for demodulation so that you get the best performance. So this is done using just checking where is the biggest eye opening. You don't need to worry about it. Polarization demultiplexing was not covered in depth in class, but just this polarization mixing matrix is unitary, and you use some adaptive filter to correct for the polarization multiplexing. And polarization basically polarization changes in a fiber due to random disturbances, but the time scales are like in milliseconds. So like some big vehicle moved, some temperature changed, or there was some earthquake, those things will change your polarization mixing, like this matrix, this alpha and 5 values will keep changing. Then carrier phase estimation is just your phase noise correction. What you do is like you try to lock onto a constellation point, like you try to estimate what is the carrier phase error, and when your data starts coming in, you continuously keep estimating like what is the uh, is phase noise that is coming in, and you try to compensate for it, because like this phase noise is a slowly varying process. Like it will if you keep correcting for it uh, like symbol by symbol, you will be able to correct, like you'll be able to compensate for it. Like for example, in a constellation, say, like if you're due to your phase noise, your constellation point here uh, along across time, like, say it keeps varying like this slowly. So what you do is like try to capture it each time instant, like what is the error that is being incurred, and if you sample it fast enough, like you will capture it as it moves only a small amount, and you continuously correct for it. So in like one like subsequent symbol, it doesn't go out of this bound and you incur no errors. So those are the impairments, and that's pretty much it. These are the signals you get. The structure, take a look like how 90-degree hybrid and how this receiver was made, and understand how these equations are coming up. That's it.
Sir, another question is, sir, here in the assignment it is written ideal 90-degree hybrid. So when discussion is going on, then in the lecture it is we have finded out 190-degree portion has been included. So ideal 90-degree hybrid structure is in the assignment one structure is drawn. This is ideal 90-degree hybrid structure.
In assignment, they have given the transfer matrix they have given, which is
No,
you are
one
supposed to.
structure is there.
The structure we have not discussed.
Sir, probably I'm not clear to you, sir. Just in lecture 3, coherent homodyne detection with 90-degree hybrid. There we have used 4 3 dB coupler and 190-degree phase shifter. Yeah. So this is the purposefully used, and ideal 90-degree hybrid structure is not discussed, but whether this is the structure which is given in the assignment, is it?
I have to find.
Okay, you can check, sir. You can check. You can reply later also. No. Yes, this structure. This structure has been discussed, sir.
Yeah, and I have not. What I have not checked is like what is the transfer matrix like. Yeah, like basically, yeah, for assignment questions there should be no trouble, but I'll find and share more details if you.
Oh, okay, sir.
Okay. And YouTube side has.
Sir, whether the transcript of the week 12 will be given soon?
We're trying, we're working on it, but
Okay.
it's going super slow. So don't have any hopes. We will try. We'll try to deliver before this
Okay.
your exam.
Okay, sir. Okay, sir.
Okay, then we can close.
Okay, thank you, sir.
Okay. See you next week. I'll try to get ma'am here next week, but yeah, no promises. We'll see.